Hello, my name is David Pollock and welcome to Spring Batch Planning, Scheduling, Execution, and Monitoring. I'm a director with Deloitte Consulting and you can see my contact information there on the screen in case you have any questions about the content or organization of this particular presentation. Our agenda for today is first to discuss the purpose of the presentation, and then to understand what it is to put together a batch schedule and what the purposes and uses of it are. Then we're going to show what a batch schedule might look like in project, as though it were a project plan. The analogy can be a very powerful one. And then we're going to show how to create the Spring Batch XML that actually drives the execution of the batch schedule. And finally, we'll look at how to track the output from the execution of Spring Batch. Okay, first, the purpose of this presentation. What this is to show you how to organize a batch schedule and how to run a set of programs to accomplish what you need to accomplish in any given evening or period where you are running programs in the background, as opposed to online, driven by user interaction. We're going to talk about how to design the dependencies between those programs so that you get the right execution sequence that makes sense for what you need to do. Then we're going to cover how to code up the XML that actually controls the execution of the batch stream. And finally, we're going to show how to represent that batch stream as a project plan. Again, I think it can be very valuable both for planning and for tracking the execution of your Spring Batch. What this is not is a presentation on how to write the individual programs, how to use readers and writers, what to do with job launchers, and so on. For that, I would recommend that you review the Spring Batch documentation. It's actually quite good, and there are a variety of texts written on that particular topic. Okay, understanding a batch schedule. First of all, there are a bunch of different kinds of relationships between programs that have to execute inside of a batch schedule. The first I've characterized as being simple. It's just a set of programs that will run independently, no relationship to one another. Any one of them can start first, second, third. Any one of them can finish first, second, and third. Neither one uses or relies on the output from another. Then there's a medium schedule. This is one where jobs are either executed serially, first job A, then job B, then job C, or you have jobs that you want to start at exactly the same time. And finally, a conditional execution if one job should execute only if a previous job has been successful. And then obviously, a complex schedule is one which has nested conditions or combinations of the previously discussed medium and simple aspects of batch schedules. So first, the simple schedule. Let's say you had 5 programs that needed to run every single night. You can either have 5 batch streams, each with 1 program in them, or you could have one batch stream that has all 5 programs in it, all launched at basically the same time. None of the programs would be dependent on one another in any way, and they can run in parallel. One can start before or after the other. It really doesn't matter. And they all run unconditionally, irrespective of the outcome of another program. Now, a medium batch schedule is where there's some relationship between the various programs that are going to execute. So, for example, let's say one job needs to follow another unconditionally. The first program might produce a report, such as report number 1. When it's through, and only when it's through, a second program might run, program 2, to produce report number 2. Might have nothing to do with report number 1, but we run it second because, let's say, there's some dependency in the database that necessitates us running it second. And then there might be a third program which, say, is an FTP program that transmits those 2 programs to some remote site. Obviously, you do not want the FTP program to run prior to the conclusion of both programs 1 and 2, and we don't want 1 and 2 to run at the same time because of contention in the database. So this would be a series of programs that need to run one after another unconditionally. Now let's see, another complexity would be where you only want a job to run if the previous job had successfully completed. So first, let's say there's a posting program that might need to run to update all of your accounts. counts. And when it's through, then you would want a printing program to produce statements based on what took place, but only if the first program completed successfully. In this case, you can see that represented on the right by testing for success and bypassing program 2 if it had not completed successfully. And now two jobs might need to run in parallel at some point. So the first job updates some accounts, and then a second and a third job produce reports running in parallel. This would be similar to the previous example, except for we can run them both at the same time because they do not have contention in the database, and obviously will get done sooner if the two jobs run at exactly the same time. So now let's look at a complex combination. You can see here represented on the screen are a series of programs and a couple of tests that would need to take place in order to determine whether or not these programs should execute and in what sequence they should execute. So we begin with program number 1. Program number 1 is executed first, just unconditionally. That's where the entire schedule starts. When it's through, success is tested. And if the program was successful, if program 1 was successful, then programs 4 and 5 are executed in parallel, which means they're both started at the same time. There's no condition with respect to when they end. It's just program 4 and program 5 are both started at exactly the same time. When both of them are through, when both program 4 and program 5 are through, no matter what sequence they complete in, we will then run program 6 unconditionally. Now if we back up to the success test, we can say if program 1 ran and it was unsuccessful in completing, then we would want to run program number 2, and then after program number 2 completes, unconditionally execute program number 3. This is an example of a complicated batch schedule. Alright, now let's talk about what a batch schedule might look like shown in Project. And in this case we'll be using Microsoft Project to represent things. So a batch schedule can be represented as a project plan. If you think of a program in a batch schedule as though it were a task in a project plan, you can see how they'd be represented in the diagram below. Each one of those tasks has a start, it has an end, and therefore it has a duration. Now, when you're planning, you may not know what the duration is. When you execute, you'll have an actual duration. That's, how long it actually takes for the job to run. Just like tasks in a project plan, programs in a batch schedule can have predecessors and successors. And they might run at the same time as another program, or they might run on their own in the same way as two tasks in a project plan might be run at the same time, or they might be run on their own. So let's take a look now at the project plan a little more closely. We have 6 programs. Program 1 executes, and then it appears as though it's followed by programs 2, 4, and 5, which all execute in parallel. And then when program 2 ends, program 3 is to execute. And when both programs 4 and 5 end, program 6 is intended to execute. This is very similar to our previous example that we were looking at as a flow diagram. Okay, so the representation becomes a real plan when we have a little bit of extra information. If you happen to know the rough duration of the jobs, you can put that into your project plan. That is your plan, not actual, but plan. And it'll begin to show you the rough duration of the entire batch schedule based on default durations that you think roughly approximate what should happen when you execute for real. So you can see by putting those durations in, we now see that program 3 will execute somewhere after midnight, or after 12 anyway. And the differences in durations indicate that program 5 runs for much longer, 2 hours, much longer than program 4, which is only 20 minutes. But again, you'll notice program 6 only begins when programs 4 and 5 are both complete. Alright, now let's talk about creating the actual Spring Batch XML. There are several parts that you need to know about when you're creating the Spring Batch XML. There are framing components, which sort of wrap the actual logic of what's going to happen in the actual schedule when it's executed. We're going to talk about what the various parts are called, the role that they play in executing the batch, what the contents of each of the different components are, and what their syntaxes are. And then we're going to show how you can group the components together to create a single schedule, and how you can put in place the right conditions that control the sequence and logic of execution of the program so that you get what you want out of the process. So first, let's look at the framing components. The part that actually controls execution have parts of the XML that come both before and after it. These standard components that provide instructions to Spring at runtime, and they also identify other resources that are required to actually execute the batch schedule. So the header itself in the Spring Batch XML identifies the references for the schedule, and it identifies the resources that are needed to execute the schedule, where resources are individual XMLs that are executed and that actually drive the particular programs that will process the data. And then there's a footing bean that identifies the task executor for the batch stream. So looking first at the header, you can see here in the green is the actual syntax for the header of the XML. It identifies schema locations, it identifies the namespaces, and so on. And again, as always, do check the Spring Batch documentation to make sure that you have the most up-to-date and correct version of the header portion of the XML statements. Okay, resources. The import statements are just to identify the dependent XMLs that are referred to in the schedule so that you get the right components identified for execution. These describe the programs themselves that will actually be executed and process the data. Each one of the programs that you're going to execute does indeed require a separate import statement so that it can be identified within the schedule. Alright, and finally the footing bean. This determines how the execution of the batch stream will actually be performed. It identifies the task executors, which control how programs will be executed. It controls the amount of resources that will be dedicated to executing the stream, and it controls the parallelism that will occur within the stream. Alright, on to defining a batch schedule. Recall that there are three different types of controls within batch streams. Serial, where one job executes right after another in sequence. Parallel, where two jobs run at the same time. And conditional, where one executes based on the completion of a previous one. We'll review each of these in turn and look at how they can be combined together in order to make pretty darn complicated batch schedules. So first of all, let's talk about scheduling a program. That's the unit that actually runs a real program. First of all, a little bit of a naming convention. Within the batch stream that we're going to define, the fundamental unit of execution is actually called a step. A step has to be given a unique name within the batch stream, and it is what identifies the actual program that's supposed to be executed. So in the example below in green, what we see is that program A is going to be executed by the step program A step. So you see the step ID is program A step. It identifies the step. The step that's supposed to follow it, according to the next clause, is program B step. And then within the definition of program A step is the identification of the job, program A, that is supposed to run. Note that program A actually refers to the XML file in the resource section of the XML that defines the job that is going to execute, probably called program A. Now, serial jobs are where one job executes right after another. So take a look at the project plan in the bottom right. We see three different green bars, one executing right after the other, ignoring the blue for the moment. So it's program 1, followed by program 2, followed by program 3. On the left now, you see the corresponding Spring XML entries that are necessary to describe that. See, program 1 step is defined, followed by program 2 step, which is followed by program 3 step. These are controlled by the next clauses. So again, looking closely, it's program 1 step runs program 1, and it's followed by program 2 step, which runs program 2, which is followed by program 3 step, which runs program 3. Each step is executed right after the previous one completes, mirroring the representation that we see of the green bars over on the right. All right, now parallel executions, a little bit more complicated. Parallel jobs start at the same time and run independently from one another. The split construct is what we use to define and frame those parallel parts of the schedule. You can see the XML here that's used to describe a split. Simply split with an ID, in this case split X, and then of course the end of the split. Everything in between there is what makes up the content of the split. Now you can have multiple parts to a split, so we see split X can be followed by something, in this case next item, and next item is then followed by next step. The following parts for a split can be either a step or it can be another split. Note the control is transferred to the next item, whatever that is, only after the entire content of the split has been executed. So let's take a look at what that looks like. Within a split, the flow construct is used to indicate what thing is going to execute in parallel with something else. So, within the first split, split X, we see that there is a flow statement that identifies group 1. And I've just used a comment. There'll be a bunch of statements in there, but these are the things that are supposed to execute on the first flow of the split. And then we see another flow, which is made up of a bunch more statements identified by group 2. Now, group 1 and group 2 will both execute at the same time, independently from each other. So all of what's in group 1 will start, that flow will start at the same time as the flow starts for group 2. When both group 1 and group 2 have completed, split X will be deemed to be complete. Now let's see what happens inside of one of those flows. So we see split X, and the first flow statement, in this case the only one in the example, but the flow statement is indicated. And within the flow we see program Y step executes, which executes program Y. And when it completes, next comes program Z step. And program Z step then executes serially after program Y. And it executes program Z. And then the step completes, and the flow completes, and in this particular case, the split completes. So that is the sequence that they are executed. Now, the flow containing program Y will start at the same time as any other flow that's inside of split X. So if there was another flow statement following this flow statement that contains Y and Z, they would both start at the same time. So in this case, in our project plan, we see that program 4 and program 5 are supposed to run at the same time. They start after program 1, okay, and when they're both completed, both of them, program 4 and 5, program 6 is supposed to then execute. So the split construct is how we indicate that. So we see something called in the XML on the left, split 2. And split 2 contains two flows. The first flow executes program 4 step that runs program 4, and the second flow executes program 5 step that runs program 5. Those two flows execute in parallel. We could redo the project plan then to show it that way. So we still see the three greens execute, and following program 1, it executes a group level item called split 2 that contains program 4 and 5 that are not dependent on each other and therefore run in parallel. And when the split completes, not when any individual item completes, but when the split completes, we then run program 6. So you can see now the project plan on the right mirrors the representation of the XML on the left. And finally, when it's all done, you can see that up at the top, split 2 has a next statement, program 6 step. So when both of the flows for program 4 and program 5 are completed, the next statement is executed, and program 6 step is then run, which executes program 6. Okay? So this flow, or this split, this split executes after program 1, and it could be that program 6 even ends prior to program 2, because split 2 and program 2 are run at the same time, and there's no dependency for program 6 on program 2, so they run independently and can finish in essentially any sequence depending on the duration of the jobs. All right, now conditional execution. Unfortunately, there's no real way to schedule a conditional execution in Spring Batch this time. So you'll need to develop a convention that allows you to have the job terminate with a code so that you can check in a subsequent program for successful execution of a prior step. And if it did not complete successfully, again, adopt a convention that says don't process any records in NetApp normally, or terminate normally without processing any records and allow the flow to continue, or some combination of those two. But you'll need to develop a convention for yourselves that take that into account. And again, notice that though batch processing might encounter an error while it's processing records, it's best to handle that error and not terminate abnormally so that the whole flow can continue. It's normal for a batch job to have an error, write it to an error log, and terminate normally. And it's good design to allow that to be true. So my recommendation would be if a batch encounters an error that it anticipates, you should note the error in a log, update the error count, and continue processing. If you encounter an error you did not anticipate, you should stop processing on that record, handle your unit of work depending on what it is that you've done, and then require operator intervention, whether it's a restart or reschedule of the job. Okay, so let's look at a complicated schedule. And this one will be pretty complete, so it's going to be rather complicated for us to walk through here. Below on the right again is a project plan. It's the same one we've been looking at. And you can see that it is for a single batch job, a single batch stream that starts with a single job called program 1, runs some jobs in parallel, and then when they're done, ends with a follow-up job. Let's look at it a little bit at a time. So we see essentially by collapsing it all down, we've got program 1, and then we've got a split that executes, and when that entire split is through, we run program 10. At its highest level, that's what this is going to do. Now, inside of there, we can see that split 1 is made up of two things, the two bars shown in red, and that's two flows. And we know by definition the flows execute in parallel. Flow number 1 actually, that's a good point. I shouldn't say that. The first flow. Flows are not numbered because numbering would imply that there's a sequencing possibly to them, and there is not. So the first flow in our definition contains program 2 and program 3. Program 3 executing serially after program 2 completes. And then if we look at the second flow, we see that it contains a split followed by program 6, and that split, called split 2, contains two programs, 4 and 5, that execute in parallel. When both 4 and 5 are through, split 2 is deemed to be complete, and therefore program 6 will be run. And then again, remember, when program 6 ends, that will terminate the second flow, and if the first flow is done also at that point, we will run program 10. All right, so how do we represent all of this in Spring Batch XML? And there it is. Now, that's a reasonably complicated representation. We're going to walk through the building of this one piece at a time to make sure that you can understand it. But that is the target that we're headed for in terms of a single definition that causes the representation on the right to be what is executed. So let's begin at the top. We have program 1, so the batch job ID, sample job. It begins with the first step, program 1 step that runs program 1. Then we have a split called split 1 made up of a bunch of stuff, and when that split ends, we then have program 10 step which runs program 10. Notice that program, or that the first split, split 1, says next program 10 step, and that will then execute program 10 step and program 10 when split 1 completes. So that's the portion that frames the entire job. So looking inside that, again, at the red bars, we see split 1. And split 1 is made up of 2 flows, and we can see those represented in the XML. Batch flow, some stuff, the end of the batch flow, and then the next batch flow, and then the end of the split. So drilling in a little bit more, we look first, again, represented by the red bars, at the first flow. So within split 1, we have the first flow. It runs program 2 step, which executes program 2. And as its next statement, it says run program 3 step, which executes program 3. So that causes program 3 to execute serially after program 2 completes. And when both of those are done, program 2 and program 3, well, obviously, program 2 has to complete before program 3. So when program 3 completes, that is the end of the flow for the first flow. The second flow in split 2, the second flow in split 1 has 2 components. First, it has something called split 2, which is going to be some programs that run in parallel. And when split 2 completes, it's going to execute program 6 step. Program 6 step then will execute program 6. Okay, and that's what makes up this second flow of split 1. When we drill in just a little bit further into split 2, we see split 2 is made up of 2 flows. The first flow runs program 4, and the second flow runs program 5. When both of those are through, split 2 is considered to be complete, and split 2 is then followed by program 6 step, which runs program 6. Okay, you can see that on the first line in the highlighted XML. Batch colon split ID equals split 2, next program 6 step. So that brings us, we actually just now walked through all of the XML statements that make up this overall schedule. And this schedule has all the different components in it that you're likely to encounter to cause complicated execution of any batch stream. So after the run, let's say that you execute that stream and you want to know what happens. Well, guess what? You can use the same basic representation to look at the results of the stream. And XML is output from the framework that allows you to see the actual results in a very consumable format. You can build this using Cognos. It's in the database. It's very easy to do. And you can produce the actual start and end times for the jobs and the results from the job. And that allows you to create a representation in a project plan that looks exactly like what happened when you ran the schedule. We happen to have written a program that allows you to read that and generate the project plan based on it. So the output XML has 2 parts. There's a header and there's a body. The standard part up at the top in the header contains a lot of metadata and so on, the namespaces, schema references, and so on. And then you get the information that you want. You can see for each one of the items, you can see the basic start and stop times, the counts of the records processed, essentially whether it was successful, whether it failed, whether it was still in started mode or had stopped at the time. All of that's indicated in the metadata for the particular job that was executed. So the body then is the instantiation of that metadata. And you can see for each row there in the data section, you get the ID, the name of the step, the name of the job, whether or not it completed, the start and stop times, the number of records processed correctly, the number of records that errored out, and then the total number of records processed. So you can see on the right the values for program 1 and program 2. Given that information, then, we can use that to create an actual Gantt chart of what took place. So, for example, Here we see a possible execution of our previous schedule. On the left are the names of the tasks that were run. Well, I'm sorry, project refers to them as tasks, so they're the programs that were actually executed when they ran. Their duration, which is the calculation that the project plan software does based on the start and finish times. The total number of records processed, how many succeeded and how many failed. And based on the outcome of the job, whether it terminated normally or terminated in error, you can actually highlight the row and the bar to be read. Now, notice that there are no relationships indicated between the various programs. That's because these are actuals. They executed when they executed. So you can see program 1 ran for a while, and then program 2, program 4, and program 5 all started at the same time. When program 2 finished, it immediately started program 3, and that ran for, again, a while longer. And then you can see that program 5, when it completed, it started program 6. And that was the end of the split, if you'll recall. And then when both program 6 and program 3 were complete, we started program 10. So this could be an actual output based on what happened, and you can very quickly tell by referring to this project plan representation what happened during the night, how long the jobs took, when they executed, where your busy times might be during the execution, and where you might have dead times that you might consider optimizing your schedule. So, and there's the representation of the plan that we actually had put in to control the execution of the jobs versus the actuals that we see below. Of course, again, program 1 went first, and it was followed by split 1, which contains split 2 and its 2 flows. So they all start at the same time. That means that program 2, program 4, and program 5 all execute at the same time. And then within that we see when program 2 executes, it runs program 3 because those were part of that first flow in split 1. And then in split 2, we see that when the first, well, both flows of split 2 have completed, program 4 and program 5, we then execute program 6. And then finally, when both program 6 and split 1, or I should say even the second flow of split 1 and the first flow of split 1 are both completed, where the second flow is deemed to be completed when program 6 completes, we then execute program 10. So in conclusion, I'd like to summarize by saying, obviously, we can create complex batch scenarios. We can implement and support them through Spring Batch. It's best to think of these complicated scenarios as though they're a project plan where each of the jobs represents a step in that plan. You can do nesting of splits and flows and steps, which is a great thing, and that allows you to create very complicated relationships between jobs. Just make sure that you observe the basic syntax of each of the individual pieces of that XML construct in order to make it all work. And finally, make sure that you understand the relationships prior to coding up your XML, the relationships between each of the different components of the XML. And again, I think that representing it as a project plan makes it so much easier to visualize what it is you're going to do when it's a complex batch stream that you need to define. So it gives you the opportunity to essentially design twice and build once. Thank you very much. This has been Spring Batch Planning, Scheduling, Execution, and Monitoring, and I'm David Pollack.